Ever looked up at a giant metal bird in the sky and thought, how the heck does that stay up there? Don't worry, you're not alone. Today, we're going to break it down step by step so by the end of this video, you'll know exactly how a plane stays up in the sky. Section 1. Forces acting on the plane. For an airplane to take off, stay in the air, and land safely, there are 4 fundamental forces which interact. These 4 forces are lift. This is the upward force which goes against gravity. Thrust, which is the forward force produced by the engines of the plane. The diagram of the plane engine may seem complex, but I'd be happy to explain it in another video. Let me know in the comments if you'd like a detailed breakdown of how the engine produces the energy needed to create thrust. Back on track with the video. Drag, which is air resistance pushing back against the plane. Slowing it down, and finally weight. This is simply the force of gravity trying to pull the plane downwards. Think of these forces as balancing acts. Lift and thrust are forces which act to keep the plane moving in the air, whereas drag and weight are opposing forces. Without managing these respective forces, flight would not be possible. The forces do not just interact, but they do change dynamically as the plane goes through different phases of flight which we mentioned before, such as taking off, cruising in the air, and landing. An example being during takeoff, the thrust produced by the engines must be greater than the air resistance and lift must be overpower the weight to achieve ascent. Section 2. How lift works. Lift is the key to overcoming gravity, and it all starts with the shape and dynamics of the airplane's wings. The wings are designed with a curved top and a flatter bottom, known as an airfoil. This design causes air to move faster over the top of the wing than underneath it, creating a difference in pressure. This is significant as according to Bernoulli's principle, faster moving air has lower pressure. The higher pressure beneath the wing pushes upward, generating lift. However, there's more to lift than just the airfoil shape. The angle at which the wing meets the airflow, called the angle of attack, plays a significant role. A small angle allows smooth airflow and consistent lift, while increasing the angle can amplify lift up to a point. When the angle of attack increases, meaning the wing is tilted more upwards relative to the airflow, the air on top of the wing has to travel faster over a greater distance to reach the back of the wing. This faster airflow increases the pressure difference between the top and bottom of the wing, leading to more lift. Remember, according to Bernoulli's principle, the faster the airflow, the lower the pressure. As a result, the pressure at the top of the wing becomes lower than the pressure at the bottom of the wing, generating lift. If the angle is too steep, the smooth flow of air breaks down, creating turbulence and causing a stall, which drastically reduces lift and could cause a loss of control. Lift is also influenced by the speed of the airplane. Faster speeds result in greater airflow over the wings, increasing lift. This is why airplanes require significant thrust during takeoff, to achieve enough speed for the wings to generate sufficient lift to counteract gravity. Lastly, the surface area of the wings impacts lift. Larger wings can generate more lift, which is why cargo planes and gliders often have wider wings compared to fighter jets. Engineers carefully balance wing size and shape based on the airplane's purpose, whether it's for carrying heavy loads, achieving high speeds, or maximizing efficiency. To summarize, lift is the result of a combination of factors. The airfoil shape, angle of attack, speed, and wing surface area. Together, these elements allow airplanes to overcome gravity and stay airborne. Section 3. The role of thrust. While lift keeps the airplane in the air, thrust propels it forward. Jet engines produce thrust by drawing in air, compressing it, mixing it with fuel, and igniting the mixture. The hot gases expand and are forced out of the back of the engine, pushing the airplane forward. This principle is based on Newton's third law. For every action, there is an equal and opposite reaction. There are different types of engines used in aviation, including turboprops, turbofans, and turbojets, each suited to specific flight conditions. Turboprops are efficient at lower speeds and are typically used for smaller regional flights, while turbofans are common in commercial airliners because they balance efficiency and speed. Turbojets, on the other hand, are used in military and high-speed applications where maximum thrust is required. Thrust is not just about propulsion, it also plays a key role in maintaining lift. Without sufficient forward motion, the airflow over the wings would not be enough to generate the lift required to keep the airplane airborne. This is why engine reliability and performance are critical to flight safety. Section 4. Managing drag. As the airplane moves forward, it encounters drag, the resistance caused by air friction. To minimize drag, airplanes are designed to be aerodynamic, allowing them to cut through the air with minimal resistance. The smooth surface of the airplane and its streamlined shape play a significant role in reducing drag. There are two main types of drag. Parasite drag, caused by the airplane's shape and external components like antennas, landing gear, or rough surfaces. The faster the airplane goes, the more parasite drag increases. Induced drag, a byproduct of lift, occurring when airflow around the wingtips creates swirling vortices. These vortices create resistance, especially at lower speeds. Winglets, the upward curves at the tips of airplane wings, are one of the most effective solutions to induce drag. By disrupting the vortex formation, winglets improve fuel efficiency and allow airplanes to fly farther with less fuel. Drag is also influenced by altitude. At higher altitudes, where the air is thinner, drag decreases, which is why airplanes cruise at high altitudes to save fuel. Section 5. Gravity and stability. Gravity is always pulling the airplane down. To counter this, lift must equal or exceed the weight of the airplane. This balance ensures that the airplane remains stable during flight. Stability is achieved through careful design and the use of specific airplane components. Horizontal stabilizer prevents the nose from pitching up or down uncontrollably. Vertical stabilizer keeps the airplane's nose aligned with its direction of travel, preventing yaw. Modern airplanes are equipped with advanced flight control systems, including autopilot features, that help maintain stability and reduce pilot workload. These systems can make tiny adjustments to the control surfaces to counteract turbulence or changes in airflow. Additionally, the distribution of weight within the airplane plays a significant role. Engineers carefully calculate the center of gravity to ensure that the airplane is balanced. Shifting too much weight to the front or back could make the airplane harder to control. Section 6. Steering the airplane. Once airborne, the pilot uses various control surfaces to steer the airplane. Ailerons. Located on the outer edges of the wings, these control roll by tilting the wings. For example, raising the left aileron and lowering the right will tilt the airplane to the left. Rudder. Located on the vertical stabilizer, the rudder controls yaw, which is the side-to-side movement of the nose. This helps align the airplane during turns or crosswind landings. Elevators. Located on the horizontal stabilizer, elevators control pitch, allowing the nose to tilt up or down for climbing or descending. In addition to these primary controls, airplanes are equipped with flaps and slats, which are extended during takeoff and landing to increase lift at lower speeds. Spoilers located on the wings help reduce lift and increase drag when descending or slowing down after landing. Advanced aircraft also incorporate fly-by-wire systems, where pilot inputs are translated into electronic signals that adjust the control surfaces. This system improves precision and reduces the weight of mechanical components. Well, now you know exactly how airplanes are able to fly. It's because of a delicate balance between lift, thrust, drag, and weight, which are all orchestrated by skilled pilots and precise engineering. Thank you for staying and watching this video. This project is one of my first and surely not one of my last. I will be creating more videos and in future improving the quality of the videos made. It will be greatly appreciated if you guys like and subscribe to help support the making of videos like this and comment on the video, what should I improve on? Again, thank you for watching. And remember, understanding flight isn't at all really complicated. In essence, it's just physics. Feel free to share this video and subscribe for more engaging content.